Hello and welcome everyone back to my third tutorial about transformers. In the first tutorial we got familiar with transformers, what they are and what advantages and limitations do they bring. Also, we implemented the positional embedding layer in TensorFlow. After the first tutorial, in second tutorial, we implemented the add a norm, base attention, CrossAttention, GlobalSelfAttention, and causal self-attention layers, and we didn't forget our feed-forward layers. And you can check these tutorials in my website pylessons.com, and there are the two tutorials that covers the introduction into the transformers, and I implemented all the code in TensorFlow. So using the layers from all the previous tutorials, we'll implement the encoder and decoder layer that will be used to build a complete transformer model that will build, compile, we'll see the summary of it, and we'll be able to use it in a standard way with a fit function in TensorFlow. Or we also could use it in evaluation mode. While implementing and testing code in this tutorial, I will not show the essential imports from the previous tutorials, so if you're testing everything by yourself, I do recommend to follow my previous tutorials and import the necessary code. So in this part, we'll begin with the encoder layer that builds the whole encoder. So let's go to the code. We'll start with this encoder layer. And you may ask why it's called encoder layer. Well, basically because it's a single layer of the encoder, and the encoder is composed of multiple encoder layers. The similar structure is in the decoder, but we'll come to this. So right now you should see the image, and I marked the encoder layer in red, and on the left side you should see n multiplied by x, and this means how many encoder layers we use in whole encoder. And basically this layer consists of two sublayers. The multi-head attention layer, well, that's more specifically to global self-attention, and feed-forward layer. And each of these sublayers has a residual connection around it, followed by a layer normalization. Residual connections usually help to avoid the vanishing gradient problems in deep networks if you already are familiar with neural networks. So basically, let's go straight to the code and implement everything quickly. So right now I already implemented everything in code. You just need to follow it along, and you might see that I created this kind of object encoder layer, and it's very simple. If you followed my previous tutorial, you may be already familiar with a global self-attention and feed forward, and I'm not going back to note everything about them. So we simply create these two layers inside of init, and then we use these layers in the encoder layer. Well, actually I already implemented it, so I simply pressed build it, run, and everything should be fine. And let's go next. What's essential is that to make sure that they work as expected. So we'll test all of these layers. So in all my previous tutorials, I use some kind of techniques to give some input to these layers to test them out. And it's not necessary to have a specific task to test these layers. So I simply create a random numbers that we push into this layer. So basically, you might see that I created already a simulation of data that I would use. So for example, encoder vocabulary size is 1000 and the model is 512. And we create this positional embedding layer that into this we feed this our that said tokenized sentence of integers, and we receive embedding layer. This means that our tokens are vectorized. So we simply pick this input and feed this output into the encoder layer. And well, let's run this code and you should see what is the input and output, because it's most essential right now for us. And you might see that embedding layers shape is here, and what is the output of the encoder layer. And actually it's the same shape, and that's the main idea what we were expecting. In a moment we come to the encoder and you understand why we need the same shape. So it will be pretty quick because I already wrote all the code, not to waste your time and mine explaining everything step by step. So right now we'll use this layer inside the encoder layer. The encoder has integrated the positional embedding layer, the multiple of encoder layers, and the dropout layer. The output of each encoder layers is passed to the next encoder layer. The output of the last encoder layer will be the output of the whole encoder. In the following image, you can see the encoder marked in red. And we will wrap all this and we'll create the encoder, and it will be very easy to use this layer later. So basically, I don't need to talk a lot about this, and we can move on to the code of this layer. As before, I created another object called encoder, and we simply we will run this right now, and you might see that it integrates a lot of attributes as the model, the dimensionality of the model, number layers, how many layers of this encoder layer we want to use, the positional embedding layer, the encoder layers, as I mentioned, and of course dropout. As before, we simply create these layers here, and on the next step, what we need to do is simply to run the inference on these layers. It's so-called forward pass. So let's test this out. We'll use the same random inputs as before, and as input we'll generate a random sequence, which would be the sequence of tokenized words in your real world, in a real example. But right now it will be not a real. So yeah, I already press to run this, and let's go to our test code. And if I run this encoder vocabulary, well, that's actually the same as before. We create the encoder with all the parameters we are interested, and here we will receive the encoder layer. And so we generate this random input that we are interested, and we pass it into the encoder layer. So let's run this. That's great. And right now we can see the result. And as you can see, for example, this random encoder input might be our single sentence, for example, Spanish sentence tokenized in characters or in word level. That must be integer. And then when we pass it through, it goes through the positional embedding layer, where these integer numbers they are vectorized. And we simply pass it through. Then goes the dropout layer to make it trainable better. And then we simply pass it through all the encoder layers that we have declared in our encoder. And that's it. And we receive the input, and finally we receive the output. And right now, this is all this implemented in single encoder layer. And output is this line received here that goes into the decoder. So that's great. You might see that it's pretty simple and we don't need to understand everything deeply. Code speaks for itself. So we can move on to another part, the decoder layer. And this layer is very similar to encoder layer, but it has an additional cross-attention layer that I introduced you in the previous tutorial. And it's between the causal self-attention layer and the feed-forward layer. Well, actually, you can see in the following image, I marked this in red. So this cross-attention layer calculates the attention weights between the decoder input and the encoder output. The causal self-attention layer calculates the attention weights between the decoder input and the decoder output. And the feed-forward layer transforms the representation of the input sequence into a more suitable form for the task at hand. So let's go to the code. I already also implemented this decoder layer object here, and it's a little different from the encoder. Let's look at it. Let's do a short analysis because it's a little more complicated than the encoder. So we have implemented this decoder layer. The decoder layer consists of the three sublayers: causal self-attention layer, the CrossAttention layer, and the FeedForward layer. Each of these sublayers has a residual connection around it, followed by layer normalization. The output of each sublayer is layer normalization of the previous two layers, and the output of the decoder layer is the same as the output of the FeedForward layer, which has the same shape as the input. If you take, for example, the translation task from Spanish to English, the context here would be a Spanish sentence and the X would be an English sentence. At the first iteration, we don't have any input to the decoder except some start token, and we have a complete sentence for the encoder. So we input these to this layer. Then it calculates the attention weights between the decoder input and the encoder out. Then it calculates the attention weights between the decoder input and the decoder out. Then it transforms the representation of the input sequence into a more suitable form for the task at hand, then it outputs the result. After the first iteration, we now have, for example, start token and the hello word as output from our decoder. So we repeat these steps until the end of the sentence, and after all iterations, we have translated the sentence. For example, as a result, we receive start token, hello, how are you? And then we'll receive the end token. That's the whole idea of iterations in the decoder. So basically, as you can see, in code, it looks very easy. We pass the X into causal self-attention. This represents this part of the code. And at the second part, we pass the output to the cross-attention layer. And here is the encoder output and goes here as input. And lastly, we pass it to the feed-forward layer and we receive X, and we push this as output of the encoder. So as before, we need to test this layer. So I run this, it should be fine without any errors, and we'll generate a random integers list, which will be our tokenized sentence. Then we'll push this data into our embedding layer to give us embeddings for each token. And then we'll push this data into the decoder layer along with the encoder output and get the output. So let's do this. We define these variables, the decoder vocabulary size, for example, dmodal, DFF, numheads, and etc. And we define this decoder layer. And then we create this random decoder layer input. And then we push this through the decoder embeddings layer. Because this will be implemented in decoder, we need to do this right now, and later we'll simply do everything inside decoder. And so we receive the decoder embeddings, and we have an encoder output. I am not creating this here, but simply we received already before as we were testing the encoder layer. So we'll run. And here we receive the decoder layer output. So let's run this and let's look at the shapes we receive. So here we have this output. It's exactly random because the input is exactly the same as I defined it, the shape. So we vectorize the sentence and we receive the embeddings, and we feed this together with encoder output and receive an output exactly the same shape as our decoder embedding. Well, that's great. That's exactly what we were expecting. So now it works, we tested it, and we can move on to the decoder layer, which is very similar to the encoder layer. The decoder has integrated the positional embedding layer, the multiple of decoder layer, and the dropout layer. The output of each decoder layer is passed to the decoder layer. The output of the last decoder layer is the output of the decoder. So in the following image, you might see everything marked in red, what we are developing and writing in code, what wraps the decoder. So simply let's move on and let's run this decoder layer to create this, and you can see that here I have a positional embedding layer, dropout layer, multiple of decoder layers, and that's it. Here we specify how many decoder layers we'll use here. And this is the D model that simply represents the size of our decoder-encoder architecture. And that's it. And as you can see here, I'm running this through the positional embedding layer. Then goes the dropout layer, then multiple of decoder layers, and that's it. You might see here that there's no feed-forward layer, right? So it's already integrated inside this multi-head attention layer. So we don't need to do this separately here right now. So that's great. Right now you can see how it works and etc. And this is simply for plotting the results if you want to debug something or etc. or to visualize the attention weights. But we don't need to worry about this right now. So what happens here? The decoder object requires two input token ID sequence represents the target sequence and the encoder input sequence, also known as context. And the decoder layer has multiple these decoder layer instances that perform various operations on the input sequence to produce an output sequence. When the decoder object is initiated, it sets up several layers such as positional embedding layer, responsible for adding positional information to the input token IDs, and a dropout layer for regularization, and a stack of decoder layer instances. The input token IDs go through the positional embeddings and dropout layers during forward pass. Then for each decoder layer, the input undergoes CrossAttention, and the feed-forward neural network layers. The output of the last decoder layer is returned as the final output of the decoder. And of course, as I mentioned, the last attention scores attribute stores the attention score from the last decoder layer, which can be valuable for visualization or debugging. And as before, I wrote some simple test code to test this layer, and we'll use the same random inputs as before and we'll generate a random sequence. So let's move on to this test code, and you might see that it's pretty similar to what we saw before. We use the same vocabulary size, demodel, and etc. And we'll use random decoder input here and etc. So here's our decoder layer, and we are interested to see what's the output of this layer. So let's run this, and we might see the output. This was our integers, for example, tokenized sentence, and here is our representation of decoder layer. And now we tested it with random data, but imagine if we were actual data, then we would have, for example, a Spanish sentence as input and an English sentence as output. Then we would have to translate Spanish sentence to English sentence. We would have to input a Spanish sentence to the encoder and English sentence to the decoder. Then we would have to iterate over decoder until we get the final end token. Then we'll have a final translated sentence. As we can see, the output decoder shape is 1 by 10512, and on this layer we would have to apply the argmax function to get the most probable token and pick the word from the dictionary to get the final word. But we will do this later. So basically we need to later, when we get this output, we need to use the vocabulary to detokenize again this integer representations into words. So, but don't worry about this right now. We'll move on in the next tutorial about this. So let's move to the final transformer, and finally we have implemented all the layers we need to build it. The transformer consists of an encoder, a decoder, and a final linear layer. The output of the decoder is the input to the final linear layer, and its result is returned as the output of the transformer. And the final dense layer converts the resulting sequence into a probability distribution over the output vocabulary. And if you were following my previous tutorials, you probably already saw this architecture many times, but I'm showing this right now because it will be completely implemented right now all the parts we are seeing. So we'll implement the transformer model in TensorFlow, and let's move on. And right now, as you can see, I'm not implementing this as a layer, but I'm creating this as a model. And because we want to use it in a standard way where we would like to use a fit function, evaluate function, or etc. In simple terms, we want to train it in a simple way. So the transformer incorporates both the encoder and decoder components to implement the transformer architecture. The encoder is an instance of the encoder object, responsible for taking a sequence of tokens as input and producing a sequence of contextual vectors, each representing information about specific token in the input sequence. And then the decoder is also an instance of the decoder object, which takes both the sequence of target tokens and the contextual information generated by the encoder layer as input. It then generates a sequence of contextual vectors corresponding to each target token in the output sequence. And the final layer is a dense layer used to take the output from the decoder and map it to the sequence of probabilities of the target. Then, when we'll have this constructed transformer model, we'll provide a tensor input to it. So basically, let's run this. I believe, yeah, let's run. It will be initialized. Let's move on. And when I run this model, it will give us model summary where we'll see all the details about this model. But before, let's talk about it. So this input tensor is actually a tuple containing two tensors, that context tensor and the X tensor, representing the target sequence for the decoder. When we call the transformer model, it processes the context tensor through the encoder to obtain contextual information for each token in the input sequence. It then uses this information and the X tensor to generate the output sequence through the decoder. And finally, the model passes the output of the decoder through the final layer to obtain the probabilities for the target token. The model returns both the logits, that means the target token probabilities, and the attention weight. To make this example more efficient, so for example, I'll reduce the size of layers, embeddings, and the internal dimensions of the feedforward layer in the transformer model. For simplicity reasons, the original transformer paper used a base model with 6 number of layers, 512 of D model, 8 number of heads, and DFF of 2048. However, for testing purposes, I'll reduce these numbers right now here. So simply let's run this and everything will be just great. Let's go, run. So as we can see, we received the input, and right now we know how many params has our encoder and decoder, and we might see that we have double more parameters in decoder than encoder, but because it is more complex than encoder. So this means that we have implemented the transformer model, which we can use with a standard TensorFlow fit and evaluate method. But remember that the larger your decoder vocabulary size, the larger the model will be because of the last dense layer here, because you may see it has also a lot of trainable parameters. So if you have an extensive vocabulary, you can use a smaller model number to keep the model size and then training time reasonable. Or you can use a vocabulary that is in characters, not in words. Then we'll reduce our vocabulary drastically. So that's it. You can see that it works, and we already have received this architecture of the transformer. And this is the whole idea about that transformer. Right now, we simply need to run the training, of course. So this means that we implemented this transform, which we can use in standard way. So that's it about this tutorial, and we can wrap this shortly. What I have shown you, what I have done. I provided a comprehensive journey from transformers, from understanding their basics and limitations to build the essential layers like add norm, base attention, cross attention, global self-attention. Then we seamlessly constructed the encoder layer, showcasing the power of residual connection. Then I introduced the decoder layer where I highlighted its role in sequence-to-sequence tasks, especially with the cross-attention layer. And this set the stage for developing the complete decoder layer, merging positional embedding and dropout for robust design. So finally, we received a full-fledged transformer model combining the encoder and decoder layer, and that's it. And we right now might use it to train our transformer, and we can use the same architecture in multiple various natural language processing tasks. And of course, not only in natural language, we can change some parts, for example, process the audio data for us, to classify the audio data, to classify the speech data, or whatever. This kind of architecture might be in various tasks complete, but it depends, of course, how many training data you have for a transformer, because it's way more data hungry than our convolutional neural networks, estimates, or other architecture. So basically that's it about this tutorial. I wanted to be quick and show you everything step by step, more focused on code, and I hope you like this tutorial. If you do, don't hesitate to smash the like button, subscribe, share this video, and if you have any questions, you can leave them in comments section below. And of course, we'll see you in the next part. And of course, in the next part, I believe you want to see how we need to pre-process data when we want to train this transformer model. So on the next part, I will focus more on a specific task, how to train this transformer and how to prepare data for it, and later how to use this trained model. So thank you again for watching, and I hope you like this, and we'll see you in our next part where I show you all these usable things you want to see. So goodbye and see you in our next part.